Hi, it's time for another math easy solution. Today we're going to discuss further into trigonometric substitution for integrals and now go over example 5 of the example series and solve this example, which is integral of 1 divided by square root x squared minus a squared and then dx, where a is greater than 0. So first of all, when you look at this integral, it's not straightforward how to solve this. But if we recall from my earlier videos on trig substitutions, I showed that if you have an expression in an integral such as this one here, where it's square root x squared minus a squared, then you can apply the trig substitution of letting x equals to a times it by, now it's secant theta, where basically now again, like I showed in my earlier video, we have to restrict the domain so that it's a one-to-one function, and in this case for secant theta, like I showed in my last video, this is going to be, well, theta is less than pi over 2 and greater than, well, we can't do greater than equal to in this case because it's divided by, so we can't have this bottom one. If this was 0, secant 0 is equal to 1, and then you'll have basically x equals a, and this will be a 0 here. So we would get a 1 divided by 0 inside this part here. So we can't have that. So that's why it's just greater than equal to 0. And then the second part of the domain for the secant is, or this could be less than, this is 3 pi over 2. And now this is greater than pi. Again, it's not greater than and equal to, it's just greater than, so you can't have it equal to pi because of this 1 divided by 0 scenario that you get. So when we do this now, when we get over here, solve the differential or the derivative of this part, so dx equals to a. Now derivative of secant theta, like I showed in my earlier video, this is just secant theta tan theta, and now we have to put the differential d theta there. So now what we could do is try to simplify this expression. So basically x squared minus a squared, all squared, is equal to, when we plug in the x, we get now a squared secant squared theta minus a squared. Now if we take the a squareds out, we get a squared secant squared theta minus 1. And now this is, we know the trig identity, like I showed in my earlier video, this is just tan squared theta. So we get that part, so we keep simplifying, the square root of a cancels out, so we get a, and now this part here is a square root tan squared theta. And now this equals 2, well, this square roots cancel, so we have a times it by absolute value of tan theta. And the reason it's absolute value because this is a square root function, so everything needs to be positive inside, and tan theta can be negative, so we have to put an absolute value. But if we look at our domain, if we have this theta, this is y, and this is, let's say, so we're drawing tan theta. We know that tan theta looks something like this, where this is pi over 2, and it keeps going on, repeats. And now this is at 3 pi over 2. And now recall where this is defined, and once again, now this is defined such that not only that you get a one-to-one function here, but you also have, when we evaluate this trig substitution, we get basically, if this is pi, so we're defined in this range from pi to 3 pi over 2 as this case, and from 0 to pi over 2 as in this case. So in this case, as you can see, this tan theta, which this is the curve tan theta, this is well greater than 0, so we have a plus. So basically this is greater than 0 in this range and this range, or this domain. So if it's greater than 0, we could remove these absolute values symbols, so we get a tan theta. So that's what this square root expression equals. So what we could do now, I'll just write this like that. So what we could do now is apply this all together. So we have square root dx of x squared minus a squared, this equals to, well, the dx is going to change to this, so that's just going to be a secant theta tan theta and then d theta. Yep, so that's it right there. And now the bottom part, this is just a tan theta, which is a tan theta right there. So as you can see here, this a's cancel. Now this tan thetas cancel, and all we are left with is the integral of secant theta d theta. So now that we have this, and also like I showed in my earlier video on the proof of the derivative of secant, of the integral of secant theta, this is just equal to, you can see the proof for this in the video link below. This equals to ln of absolute value of secant theta plus tan theta, and now we have to add our constant c. So that's what this integral is equal to. But now we have to, well, get back to our variable x. We have to get back to x. So to get back to this variable, well, we go x. We know that x equals to a secant theta. So we know that equals to that. So if we rearrange this, secant theta is equal to, well, just divide the a out, x over a. And we know that by definition, secant theta is equal to, well, it's opposite of the cosine, so it's hypotenuse over adjacent of a right angle triangle. So if we were to draw a right angle triangle like this, if this is the angle theta, then hypotenuse is x, adjacent is a for this relation. So we know this, and now we're using Pythagoras. This is hypotenuse squared minus the base right here squared, all square root. So we have this length there. And now what we could do is, we know secant theta, which is this. Now we just need to get tan theta. So we know tan theta is equal to, this is just opposite over adjacent by definition. So this equals to square root x squared minus a squared, all divided by, well, a. So that's opposite divided by adjacent. So that's what we have here. So now we can just plug this in. So what we get now is the integral of dx over square root x squared minus a squared is equal to, yeah, so this equals to ln, and now when you plug this in, so secant theta, that equals to just x over a, and now we have to add this plus tan theta, which is square root x minus a squared over a. All this is absolute value plus c. So now this is this has a common denominator, so we could factor that out. So what we get is ln of x plus square root of x squared minus a squared, all divided by a. And now if we recall from my properties of natural logs, this can be separated by subtracting. So this x equals to, yeah, so what we get here is just x plus square root x squared minus a squared, absolute value. Now we just subtract this out, so ln a. And again, it's not ln absolute value of a because a is greater than 0. So when we do this, this is just property of natural logs. Now we have a constant plus c, but this is also a constant, so we could just write this in a simpler form. So this is, again, write this all out, ln x plus ln of absolute value of x plus square root x squared minus a squared. Now we could do a plus c1, where basically this c1 is a constant, and that equals to, well, c minus ln of a. Yeah, and that's basically just another constant, just a neater way of writing it. Anyways, that's all for today. Hopefully you learned from this pretty extensive example, yeah, on solving this integral using trig substitution. Anyways, thanks for watching. Like always, you can download these exact notes in the link below, and stay tuned for another math easy solution.